Hello everyone, welcome to COMP125 Principles of Computing. Today we are going to continue our discussion about chapter 4, the building blocks for creating a computer, and we are going to focus on Boolean logics, gates, and how to create actually simple computer circuits using the gates that we talked about. Okay, so I'm going to first talk about Boolean logic. So Boolean logic is a branch of math that helps us to create. This is going to be the fundamentals of how we create computer circuits. The nice thing about Boolean logic is that, in fact, unlike the regular arithmetic expression that we work on numbers, adding some numbers, subtraction, division, and so on. In Boolean logic, all the possible values that we have are only two values, true and false. And we learn about different, kind of operators, just like, for example, in arithmetic expressions, we add two numbers. So 1 plus 2, the result is going to be 3. So when you only have two possible values, true and false, the operators are going to be different, right? We learn about the operators and the Boolean, the basics of the Boolean logic. And because Boolean logic only have two possible values, 0, 1, it can simply mapped to biostable environments. This is exactly the environment that the transistors and in the computer we need. So that Boolean logic then will be mapped to some electrical circuits, and then we can see that using the Boolean logic we learn how to create complicated circuits that we need. Okay, so the first topic that we are going to cover here is going to be Boolean logic. So all those binary representations, remember the binary representations that we talked about in the previous section, those are going to be a sequence of zeros and ones, right? So the nice thing about the Boolean logic is that because it has only two possible values, true and false, we can say that, okay, true will be represented, will be representing 1 in our binary representation, and 0 or false is going to represent 0 in the binary representation. So all those sequence of zeros and ones that we talked about in the Boolean logic will be mapped to trues and false. Okay, so we will talk about these things at the end. So now let me actually just go and focus on the Boolean logic. Let me actually define that and all the operators over that, and then we will come back and see that how those binary representation will be mapped to Boolean logic. Okay, so Boolean logic, as I mentioned a couple of times so far, is going to deal with only two possible values. We only have true and false. Okay, so we are going to have some Boolean expressions, just like the arithmetic expressions. The arithmetic expressions can have, different values based on the value. For example, if you have some expression like x plus 1, this is going to be a Boolean expression, right? Depending on the value of x and y, the result will be, understandable. So if x is 1, y is 2, the result here is going to be 2. But in Boolean expression, the only possible result of the expression is going to be true and false. So when you are actually just writing c is greater than 25, the final result of this expression is going to be either true or false. C is going to be either greater than 25 or it is not greater than 25. So it's going to be only true, false. It's not going to get any other possible value. Or when you are comparing A and B and saying that A equal to B, the final result is going to be either true or false. Remember, we have used the Boolean expressions when we write we talked about the algorithm and the conditional statements in front of all the conditional statements that we wrote in chapter 2. we wrote a Boolean expression, right? Or for the termination of the while statement. So you have already seen that Boolean expressions. So Boolean expressions can be more complicated, not only just a simple expression like C greater than 25. This is a simple Boolean expression, but you can create a more complicated Boolean expression using some operators that we in Boolean logic, the main three operators that we have are going to be and, or, and not. Okay, so in arithmetic expressions, the main operators that we have are going to be, addition, subtraction, division, and multiplication. In the Boolean logic, we have three main operators and, or, and not. Okay, so here you can see that it is a more complicated Boolean expression that has been created by adding this Boolean expression to this Boolean expression. At the end, I'm going to actually later on talk about all of these operators, how the and is going to work, how or is going to work, and how not will be actually applied. So let me discuss each of these one by one. The very first Boolean expression that we have is going to be and. We write it just exactly between two Boolean expressions. Just assume that A is a Boolean value, B is a Boolean value. In fact, it can be a Boolean expression, okay? So, and you write it as A and B. And the result, or in fact, in some actual notation, you can just write it by putting a dot between A and B. So this is also just read as A and B. So, and just like the way that we understand it in English, that you are saying that, for example, remember we wrote Boolean expressions in chapter 2 using and. For example, if x is greater than 5 and x is less than 7, when we are saying and, it means that both of these two conditions should be true, right? So and exactly is going to do the same here. If A and B, both of them are true, the result of A and B is going to be true. Otherwise, the result is going to be false. Okay, which means that if A or B, any of them is false, the result is going to be false. We only get true out of this if both A and B are true. So where this kind of operator is going to be useful, for example, you wanted to say that a number, for example, a test score like S, is in the range of 90 and 100. Okay, so for example, if the grade of a student is between 90 and 100, you are going to assign letter grade A, right? So you wanted to just write down that S is between 90 and 100. You know that in computer, S is in the range of 90 and 100 is not a simple instruction. So I have to write it, it's just like I have to break it to two conditions. S should be greater than 90 and S should be less than 100. And be careful, both of these two conditions should be true. So this is where exactly and is going to help us to write down the final expression. So you would write it as S is greater than or equal to 90 and S is less than or equal to 100, and you put and between them. So this is one Boolean expression, simple Boolean expression. This is one simple Boolean expression, and you put and between them, and the result is going to be a larger Boolean expression. So again, the final result here is going to be either true or false, but both of these two Boolean expressions should be true to make the final expression to be true. So here I wanted to introduce a very useful structure that we call it truth table. We are going to use it a lot through this chapter. What is a truth table? Truth table, in fact, is a simple table. It's a structure that helps us to write down all possible values for the inputs, and just calculate and write down the output based on those inputs. Okay, so if I have two possible inputs, and these possible inputs are going to be Boolean values, or they are going to be only true and false, the total number of possible values that I have is going to be 4, right? So let me actually just define the columns here. So on the input side of the Boolean, on the input side of the truth table, I would write down one column per input. So one column for A, one column for B. Okay, and I would write down the possible values for A and B as the rows. So each row is going to show me one possible input, a set of inputs. Here you can see that I have 2 inputs. That's why the number of rows will be 4. Why? Because you have 2 possibilities for A, right? And you have 2 possibilities for B. So it would be actually 2 multiplied by 2. The final result is going to be 4. So 4 rows in total to show all possible values. And if you read these values here, you can see that I have considered all possible values. If A is false and B is also false. If A is false but B is true. If A is true, B is false. And if A is true and B is true. So you can see that B can only have 2 possible values, right? And A can only have 2 possible values, true and false. But when you are actually combining them, you can see that in total, I'm going to have 4 possible values. So this is just like a simple, statistics, right? So 4 possible values, so 4 rows. So now on the output side, you can see that I have one column for the output, that this output is going to represent A and B. So I wanted to know that what will be the value of this expression A and B if A is false and B is false. Remember, and will be only, the result of and will be only true if both A and B are true. So by looking at A, which is false, and B, which is false, the result, I know that for this possible set of inputs, this is going to be, the result here is going to be false. How about this row? What is going to be the result of A and B if A is false and B is true? So again, A and B will be only true if both values A and B should be true. So here the result is going to be false. Here A is true, but this time B is false. So again, the final result for A and B is going to be false. And at the end, I have A is true and B is also true. So this is going to be the only row that gets the value true. Okay, so this is the full truth table for the AND operator, that you can actually see it a more nicer way here. Okay, so you only get this row as true because this is the only case that both A and B are true. Okay, the next operator is going to be OR, A or B, which is sometimes in some textbooks will be written as it's just like a capital V between A and B. This is a mathematical notation anyway. You might have seen it in previous courses of math. Or in some textbooks will be actually shown as A plus B. Be careful, this plus, it doesn't actually mean the arithmetic plus for us. This is just showing OR. Okay, what does the OR operator do? The result of A or B will be true if any of the values A or B are true. And this is, in fact, exactly the meaning of OR in English, whatever we understand as OR in English, that if weather is rainy and if I am going out, sorry, this is and. So let me actually just find if weather is rainy or if it is cloudy, in both cases I'm going to take my umbrella. Okay, So if it is raining right now, or if it is not raining but it is cloudy, I would guess that probably it's going to rain, right? So in both these cases, if one of these is true, I would take my umbrella. But if both of them are false, if it is not raining and if it is sunny, it is not cloudy, so I would not take my umbrella. So this is allowed in, if you are living in Vancouver, you would take your umbrella always. So it's not, I mean, except that you are living in Vancouver, except that you would just consider that logically. Okay, so forget about that funny example that I mentioned here. So this logical operator is going to be used in the cases that, for example, just assume that you wanted to see a student should take a specific course like Math 125, for example. And you would say that if the major of the student is math or computer science, the student should take this course. So you see that I put or, because if the student is taking, the major of the student is math, the student should take. If it is the major is computer science, it should take. So I put or between them. You don't need to have both these two to be true to the result to be true. Either of them is true, the result will be true. So if both of them are also true, the result anyway is going to be true. So it's, you know, kind of, it's just like the reverse of and. Not exact, I mean, no, I shouldn't actually say that the reverse of and. It's just, you know, I think you already actually understand that, because this is a logical actual action, that if only if both of these two Boolean values are false, the result is going to be false. Otherwise, this is going to be true. So this is the truth table for OR operation. And again, you can see that I have a truth table, that I have some input columns. I have two values, so one column for A, one column for B. All the possible values for A and B. A and B both are Boolean, so I would have at the end 4 possible rows to show all the possible values. And the truth table A or B is represented here. The possible values, the final value of A or B is represented here. You can see that if A is false and B is false, there is nothing to actually make A or B true. So the A or B is going to get false. But this is the only time that A or B will be false. On the other rows, on all of them, the result is going to be true. Because if A is false but B is true, so the OR will be true because one of them is true. If A is true and B is false, because A is true, the A or B will be true. And if both of them are true, at the end, the result is going to be true, because both of them are true, of course. So one thing again about the truth table is that sometimes you, you know, not only you can show the truth table by putting all the, these showing the values false and true, just write them, the full dictation. You can also show it using zeros and false. So zeros and ones. So all the falses will be represented as 0 and all the trues will be represented as 1. And it's going to be more readable for us after, you know, from this point on, because at the end, we are going to, in fact, think about those binary representations and the circuits, gates and circuits that we can create to create a computer. So at the end, we wanted to show those zeros and ones. So just we can convert it and show or to truth table using 0 and 1, and it basically shows exactly the same thing. So zeros for falses and ones for truths. So this was the second operator, logical operator. And the final logical operator that we have, the main operator, is going to be the not operator, or here it actually just write it as rule. So unlike and or that you had 2 operands for the operator, not will be only applied over one operand. So you would write it as not A. And what you understand from this is going to be exactly the, what we logically understand in English. Not A will actually reverse the value of A. Whatever is the value of A will be reversed. If it is true, not A will be false. If A is false, not A will be true. Okay, so for example, the GPA greater than 3.5, this is a Boolean expression, right? Either it's going to be true or false. When you actually put not behind that, the result is going to be when the GPA is in fact less than or equal to 3.5. Okay, so it can be actually showed as not GPA greater than 3.5. So a nice thing about the truth table here is that, okay, the truth table for not will be slightly different from the truth table for and or, right? You can see that the main difference here is that the number of rows are just 2. Why? Because I only have one input, right? In the truth table for for and or, you had 2 inputs, right? A and B, and then you actually just, for example, put and between them, right? A and B. So you have 2 values, so you have 2 columns. At the end, you would have 4 rows to show all the possibilities, or for example, for or. But when you are just talking about not, which has only one operand, the only possible column, input column is going to be 1 column, right? And you only have 2 possible values for that. So 1 row for 0 and 1 row for 1. Okay, so you might actually just think that what would happen if I have more than 2 values. The number of rows and columns in the truth table will depend on the number of inputs. So if you have 3 inputs and all of them are going to be Boolean, right? So at the end, the number of rows is going to be 8. And this is nice that you would actually just see that this is the number of rows will be depend on the number of inputs, and this is going to be 2 power the number of inputs. So the number of inputs, if it is 3, the total number of rows in your truth table is going to be 8. You will actually see this in the practice questions at the end of this section. I think this is going to be section 4.3.1. Those practice questions, you will see that the truth tables are going to have more number of rows. They are going to grow. Okay, so before I actually show you some example, and I'm going to actually solve a couple of those practice questions for you here. But before we do that, I would also like to talk about the precedence of the different Boolean operators. Just like in math, in usual arithmetic actual expressions, that we have precedence rules for the regular operators like plus, subtraction, addition, and division. We also have precedence rule for the the Boolean operators. So when you write, remember what is the precedence rule? When you write an arithmetic expression like this, as a human, you would understand that, okay, multiplication is going to have a higher precedence, right? So the final result of this expression for you is going to be, you first multiply 2 by 2, the result will be 4, and then you would add 3 to that, so the final result is going to be here 7, right? The reason that you interpret this expression as 7 is that the multiplication is going to have higher precedence than plus. So you would apply multiplication first and then you would apply plus. Okay? So in Boolean expressions, there is going to be some precedence operators, some precedence rules as well. And the order of the precedence rules is that not is going to have the highest precedence. So whenever you see not is going to be the highest priority, you would apply that first. And then and is going to take the next level in the precedence, and then or at the end. So or is going to be the least value in the precedence. So when you see an expression like this, you can see that I have two operators and I don't know that which one is going to be actually applied first. Should I first get the result of x and y and then apply not, or vice versa? But the thing is, from you know that not is going to have higher precedence, right? So you would apply first not. So not x will be calculated, and whatever is the result will be actually and with y. Or let me actually give you another example. If you see a more complicated expression like this, how you would actually interpret it, that not is going to have the highest precedence, right? So you would apply not over y, and then you would consider and as the most highest, as the one that have the highest precedence. So you would calculate, evaluate x and whatever is the result of this parenthesis, and then you would actually, whatever is the result of this part will be or with z. Okay, so now you can see that sometimes it would be kind of complicated to read these expressions. So it is usually recommended that always put parentheses when you are writing a more complicated expression, so it would be more readable, right? So using the parentheses makes it much easier to understand. And just like in math, that the parenthesis has in fact the highest precedence, in the Boolean logic, again, parenthesis is going to have the highest precedence. So for example, if you write down something like and B or C, okay, so because you put the parentheses, it is very clear that whatever is inside the parentheses will be calculated first, and the result will be and with A. Okay, so we will see that when we write the Boolean expression, more complicated Boolean expression, we will use parentheses, and it helps us to actually makes it readable and write down exactly what we need. So let's do a couple of practice questions from the end of this section. So assuming that x is 1 and y is 2, we wanted to actually determine what is the result of this Boolean expression. So this Boolean expression has been calculated from two simpler Boolean expressions and put and between them. So what is the result of this Boolean expression? Comparing x to y. Is x equal to y? I know that the value of x is 1, so the result here is going to be true, right? How about this Boolean expression? I know the value of y is 2, so this Boolean expression, which is comparing y to 3, is going to be false. Y is not equal to 3. So you have true and you have false, and you are applying and between them. So the final result is going to be false. Okay, so let's do another example. So first I need to evaluate this. Is x less than y? Based on the values that I have for x and y, yes, this part is going to be true. You know, the nice thing about having, when you actually are going to have a or part, is that when I get true here and I have or with something else, I don't really need to evaluate this part, right? Because this part is true. So the final result is going to be true no matter what is the value of this one. This is just because the operator or is working in that way. If the first one is true, I don't need to evaluate this part anymore. I know the final answer is going to be true. But here, just for the sake of, practice, let's just evaluate this one. Is x greater than 1? No, this is going to be false, but it doesn't really matter. At the end, the final result would be true because the first part is true. And how about this one? You can see that it's more complicated. I have two logical operators, so I would need to calculate this one first. I have x equal to 1. Yes, this is true. I need to also calculate this one because I have and. If I had or here, I would stop calculating this part inside the curly square brackets. But here I need to actually just calculate this one as well. Y is equal to 2, right? So this is going to be true as well. So you have and between them, true and true. So the result inside the the square bracket is going to be true. And then you would apply the not operator over that. Not will reverse the result. So the final result here is going to be false. Okay, let's do one more practice here. Question here. It's just asking that assume I have 3 Boolean variables, A, B, and C. I wanted to so these are going to be Boolean, so the only possible values for them are going to be true and false. So it's asking to create the truth table for these expressions that I have. I have 2 expressions here, A and B. Let's just create a truth table for each expression. Before write down the final output column, one thing that I noticed here is that instead of only having, the number of inputs is important for me, right? The number of inputs here is going to be 3, A, B, and C. I have 3 inputs, and remember, when I talked about the truth table, the number of rows in a truth table that you have 3 inputs is going to be depend on the number of inputs, right? 2 power the number of inputs. So the number of columns that I have is going to be, the number of input columns that I have is going to be 3, A, B, and C, okay? And the number of rows is going to be 2 power 3. I have 2 possibilities for A, 2 possibilities for B, and 2 possibilities for C. So in total, it's going to be 8 different possibilities. And when you are writing the rows, you should be careful that you write down all those possibles. I know that when you are writing 8 different possibilities for all this, it might be actually just complicated to keep track of all different possibilities that you have written. But let me actually give you a trick. All of these values are going to be only 0 or false, or true or false, right? One way to do it is that just do it 1 column at a time. So what I'm doing here is that I know at the end I'm going to have 8 different rows. So for these 8 different rows, I know that for 4 of them, A will be 0, and for 4 of them, A is going to be 1, right? So I will write down all of them here, all the zeros first, and then all the ones. Okay? So this is for A. Again, for B, I would have 4 rows that I have 0 for B, and 4 rows that I have 1. But I should actually be careful. If I write it down this way, just like A, I am missing the possibilities, right? It's just like A will be exactly like B. I wanted to make A different than B. I mean, not different in terms of, different values. But the order of these zeros and ones should be different. So what I'm doing here is that I would write it in terms of, 2 zeros first, and then 2 ones, and then again 2 zeros, and then 2 ones. Okay, so now you can see that if you look at any of actually these rows, you would get different values for A's and B's. So what I'm doing for C again is that I would need 4 rows to be 0 and 4 rows to be 1s, but to make them completely different than the representation for A and B, I would write them as alternative zeros and ones. 0, 1, 0, 1, 0, 1, 0, 1. So now you have, if you look at each of these rows, you would see that I have written all the possible values for A, B, and C. So this row, the very first one, is showing that all of them are 0. This one is showing that A and B are 0, but C is 1. This one is showing that A is 0, B is 1, C is 0, and so on. So it's just actually a trick to show you all these different values, all these different possibilities. And the other way to think about it, again, is that when you have 3 variables, all of them are going to be Boolean, so 0 or 1, true or false. You can just think about it as all different values from 0 to 7, right? And think about the binary representation for them. So basically this one is the binary representation for 0, this one is the binary representation for 1, this one is the binary representation for 2, and so on. So these things that I'm saying is just, some tricks to help you to don't really memorize it. It's just understand it and digest it, and you would never forget that how to create a truth table in this way. So the order of these input values at the end is not really important for me. You can just write it as C, A, B, or whatever. At the end, you are going to have 3 different columns and 8 different rows at the end. So whatever is the inputs, the number of rows will be depending on that, and just make sure that you have exactly, completely different rows for each possibility in the final, truth table that you have. Okay, so I think I have been talking about the truth tables quite a lot so far. Okay, so this part was just showing the inputs, and I got all the columns, all the rows and possible inputs for them. So now let me actually just write down what is the output here. At the end, we were going to create the truth table for these expressions. This is one expression and this is another expression. So let's actually do one at a time. The first expression, it will be not A and B or C. Let me actually write down this one here. So the final expression that I'm looking for is, if I don't forget that, would be not A and B, and at the end get the result. Okay. And B, and the final result, or C. Okay, so if I write down this one on the output column, it might be actually just very complicated, right? So as simplest, I can actually just break down and, created one column for each sub-expression that I have. I have one sub-expression here. I have one sub-expression here. And I have the full expression at the end here. Okay, so I would write down not A as a one column, as one output column. So it will, at the end, it actually makes it much simpler for me to, calculate the a column for the output. And so let's first actually calculate it not A. So not A, you can see that this column is just working on A as the input. So doesn't matter what is the value of B and C, you just look at the value of A. Because this is 0, not A will be 1. A 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 is 1, not A will be 0. 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 Okay? So then I'm going to actually just take care of this sub-expression here. So this is going to be not A and B. Okay, so for this column, because I have one column for not A, I don't need to actually go and look what is A. I just can simply just refer to this column, okay? Not A and B. So the only input for this column is going to be this column and this column. So you wanted to calculate not A and B. Let me actually just use a different color here, maybe. It's makes it more readable. Okay, so you look at B. B is 0. So not A, whatever is not A is 1. The result anyway at the end is going to be 0. B again here is 0. Not A is 1, but the result is going to be 0 because B is 0. B is 1. Not A is 1. The result here is going to be 1. B is 1. Not A is 1. The result here is going to be 1. B is 0. Not A is 0. The result is going to be 0. B is 0. Not A is 0. The result is going to be 0. B is 1, but not A is 0. The result is going to be 0. B is 1, not A is 0. The result is going to be 0. Okay, so I'm done with this column as well. So now I can, because I have this sub-expression here, it's going to be much easier to calculate the final expression, which is going to be whatever is the value of this, or C. So I would consider that as the last column and the final output that I'm actually just looking for. So let me just clean up a little bit here. And let me just go back and, okay, write a different color here. So the final column that I have is not A and B or C. So I have not A and B here. So I don't need to take care of the full actually set of columns. I just need to consider this column and this column. You can see that I just break down that complicated expression to smaller expressions so that at each time I just need to take care of two columns. For example, when I'm applying and, I would just apply it over two columns. I don't need to be careful about a couple of multiple actual columns at a time. At each time, I would just take care of two columns. So now I would just focus on this column and this column, and you are going to get or between them. So C is 0. This column is also 0. So the final result is going to be 0. This is false. 0 means false, right? This is false, this is false, the final result is going to be false. C is 1 or true, so because you have or, it doesn't matter what is the column here, which is 0, the final result for this row is going to be 1. C is 0, but this column has the value of 1, right? So the final result is going to be 1. C is 1 and this part also is 1. So the final value for this part is going to be 1. C is 0. This column also is 0. So this is going to be 0. C is 1. This column is 0. But the result is going to be 1 because C is 1. C is true. C is 0 or false. This column is also false. So the result here is going to be 0 or false. This one is C is 1 or true. The value of this column is 0, but the result is going to be true or 1 because C is 1. So this is going to be the final truth table that I have. So let me just clean up this one, make it look nicer. Okay, so this is the final one. You can actually create it just like that. You can create another truth table for the this part of the question. Again, whatever you just need to create the truth table with exactly 3 input columns, 8 input rows, 8 rows in total actually to represent all the possibilities. Write down the values for A and B and C, and then just break down this expression to first create a column for this one, then create one column for this one, then create one column for the full actual expression. So by this breakdown, you would actually make it much easier to calculate at the end. I think this one has been represented. I mean, this is, I forgot that I had that one added here, but anyway. Okay, and the final practice questions that I have for this section is, it's asking that, for example, you have a Boolean expression like this, and I wanted to know that when this Boolean expression will be false. Okay, so basically I wanted to know that what will be the value of A and B that makes this Boolean expression false. How to solve a questions like this? What you can actually do here is, again, use the truth table. Create a truth table and create, find, calculate the full expression, okay? And at the end, what you only need to do is to just look at the final column for this expression and see that where you are getting zeros, as false, right? So then look at the corresponding values of A and B in that row that makes the full expression false. So what I need to do here again is to just create the truth table. Let me actually just do it quickly here. You can see that I only have 2 input values, A and B, so the number of rows is going to be 4. So 0, 0, 1, 1, 0, 1, 0, 1. Just all the possible values, right? So A or B, this is one sub-expression, right? A or B is going to be 0, 1, 1, 1. Okay, and one sub-expression for this one, not A, one column here. So it's going to be 1, 1, 0, 0. And the full expression is coming here, A or B, or not A. So I need to focus on these 2 columns. So this column is 0, this column is 1, false, true. So when you get or between them, this is going to be true. This one is going to be true as well. This one is going to be true as well. This one is going to be true as well. So when you are looking at the final, the column of this expression, you can see that all the values is always 1. There is no row that is getting 0 or false, which means that it doesn't matter what are the value of A and B, this expression is always going to be true. It's not possible to make this expression false. Okay, if you had some other expression that you had some, for example, some 0 in that, for example, something like this, when this expression will be false, here is one possibility that makes it, here is one possibility that is false, and here is one possibility that is false. You can just go back and look at this. When all the values of A, B, and C are zeros, this expression will be false. When the values of B and C are 0, but A is 1, again, the value is going to be, the expression is going to be 0. And when the value of C is 0, but the value of A and B, both of them are true, it's also going to be 0. So truth table is your friend. Okay, so get used to it. Do a couple of practice on writing down the truth tables. Later on, we will see that even when we are, designing the circuits, we need to write down the truth tables to be able to create the, more complicated circuits for us. So I'm going to, let me actually just finish the next subsection as well. Then I will stop this video. Okay, so far we learned about the Boolean logic. But why we talked about the Boolean logic, why Boolean logic is interested, appealing to us, because we are going to create our final computer, the mechanical computer, using, this Boolean expression. So at the end, I'm going to actually just tell you that it is possible that all of those operators that we talked about, or, and not, these operators can be, we can actually create some circuits, some electronic devices to represent, to actually act just like and, or, and not. So what are those actually devices, those electronic devices that will operate this and, or, and not? They are called gate. So from now on, whatever we are actually going to work over is going to be gates. You don't need to be worried about how the gates has been actually implemented, but this picture, figure 4.18, is showing that how in fact we create, for example, a very simple gate NOT. So you can see that it has been created using some transistors and resistors. So it's more like a, physics and electronics. I'm not going to actually just talk about the details how it is possible to create that, but this figure shows you that yes, there is some physics behind that, and it is possible to create gates for or, it is possible to create gates for and it is possible to create a gate for not. Okay, so all of these different operators, Boolean operators that we talk about, we can create some physical devices that we call them gate for each of them. So, but we, in our designs, what we are going to, how we are going to show these gates, we are going to show them, using these diagrams. So graphically, we are going to show gate and using this, figure, or using this figure, and not using actually this figure. So you can see that the number of inputs for the gate, just like an operator that we have, there are going to be some input and some output. So you pass on some input to the gate and you get out an output from the gate. So you can see that for all of these different gates, 3 different gates that I have, I only have one output, right? One wire that shows the output. If you have a binary gate, just like a binary operator, the AND operator, which is, we call it binary because it has 2 input operands. So I have 2 input wires coming inside this gate. You can see that I'm showing the one input as A, the other one as B. So their final result is going to be A and B. So what does the gate in fact do is that if you send, some voltage here as A, which represented 1, and some voltage for B in the wire that represented 1 again, after you passing it through this gate, this wire, the voltage on this part, on the output side, is going to be 1 as well. Okay, so it is possible, physically, electronically, it is possible to create such a gates. But we don't want to actually go to the details how we created them, because the course is not about that. I just wanted to actually show you that, okay, it is possible, and from now on in our designs, we are going to refer to these gates, 1 gate for AND, 1 gate for OR, and 1 gate for not. And they are going to exactly, be corresponding to and, or, and not operators in the Boolean logic. So in your course, in your textbook also, it has been talking about two very interesting gates, NAND and NOR. NAND is exactly the not and, NOR is not or. So it's just like, the abbreviation for not and, that we call it NAND, and not or, and we call it NOR. Why these gates are important, interesting, the reason is, when we are designing the gates for and, or, in fact, NAND, which is not and, can be created using two transistors, but and needs to be created using three transistors. Okay, so you can see that, yes, NAND, which is the not of and, needs less number of transistors. So it will be, cheaper to create some circuits using this type of gates instead of using and. NOR is just like exactly and. I just noticed that I have a typo here. This is NOR. But forget about that. I'm in detail. Okay. So NAND and NOR, the only thing that is about them is, actually computers will be using NAND and NOR, not and or basically. But because it's going to be more complicated for you, inside the text, we just actually keep talking about and or, and we are going to completely forget about NAND or NOR. But just know that because NAND and NOR are going to be cheaper than and or, okay, because you can see that these figures shows you that they need less number of transistors to be created. So they are going to be cheaper. They are going to be really used to create the final circuits to create an actual computer. But the logic behind them is not that much different. So to make it much easier for you to understand, we are going to just using the and, or, and not. So just know that these gates are, exist, but don't need to be worried about them in the context of this course. Okay, so I'm going to stop this video here and talk about the rest of it in another video.